morning. As you know, there are many issues with shale. I'll give you a few things that we think we know about shales, but I'll also highlight a lot of questions that need to be resolved, and hopefully some of them will be done in the course of this project. And I'll be covering a few topics very briefly. What is a shale? A few comments about shale permeability, shale brittleness, some of the seismic or acoustic properties of shale, a few words about shale anisotropy, and then a few words about the special challenges of organic-rich shales. So first of all, what's a shale? A lot of people have a lot of definitions, but I think the most generally accepted one is that it's based on size. A shale is a rock that is composed of mud-sized particles, and that means particles that are 30 microns or smaller. Now notice that that is a size definition, not a compositional definition. And that itself is one of the reasons why characterizing shales is such a challenge, and why it's hard to find, well, maybe impossible to find unique geophysical indicators of shales. Because some shales might be clay-rich, others can be calcite-rich, others can be quartz-rich, others can be organic-rich, and of course, all combinations of that. So their elastic moduli, Poisson's ratio, and so on can be extremely variable. And of course, in the literature and in the business, there are a lot of other ways that we use these words just to be careful of. Sometimes people only use the word shale to mean those mud-sized particle rocks that split, right, that are laminated and fissile. And in that case, maybe people would use the word mudstone to refer to the more amorphous mud-sized particle rocks. And siltstone, again, if it's consisting of those mud-sized particles, siltstone might refer to those rocks that have low clay fractions or hard, high silica content. And even in high calcium carbonate rocks, we encounter the word mud, which can refer to a lot of micrite. In other words, these micron-sized particles that could be pure calcium carbonate. So again, be very careful about interpreting minerals from the word shale. Of course, shales are known to have very low permeability, and one simple way to understand that is in terms of the Kozeny-Kármán relation. Kozeny-Kármán relation is a kind of a semi-theoretical relation that tends to work pretty well. It actually comes from a rigorous derivation of flow through a rock, but a rock that has ideal circular pipes flowing through it. And of course, real rocks don't have round pipes unless we drill them. But what's been found over the years is still the scaling that comes from the Kozeny-Kármán is still relevant. And so what it tells us is if kappa is the permeability, then certainly permeability increases with porosity, and it's a strong dependence, porosity to the third power. It decreases with tortuosity. Tortuosity is just a measure of how complicated the connectivity is. If we had a lot of nice straight flow paths for our pore fluids, tortuosity would be 1. But in any real material, the fluids have to go around this grain and under that grain and maybe connect to that crack. And so the tortuosity grows. And typically, it's not something we measure very accurately, but typically we think of tortuosity being something like 2 in a real rock. So finally, the point I want to make here is this very strong dependence on the grain size or the particle size. That's what I use the letter D for. And so let me illustrate it with this map that came out of the old book by Bourrier and company. Vertical axis is permeability, horizontal axis is porosity, and those authors kind of mapped your typical porosity perm regions for different kinds of rocks, ranging from clays and shales, in other words, mud-sized particles down here, up through silts and sandstones, coarse granular limestones, and so on. So if we just follow one vertical line, like this dashed line at 10% porosity, then obviously the porosity is staying exactly the same as I go from bottom to top. But as we go from clays and shales to silts and sandstones and so on, the permeability grows many orders of magnitude. Right? This is a logarithmic scale. So just a reminder, in fact, this has been one of our challenges for trying to find a direct seismic measure of permeability, is because seismic has been fairly successful over the last few decades in sometimes mapping porosity. Right? We talk about impedance porosity relations, and a lot of times we can do that. But we don't have any seismic measurements that directly respond to particle size. To some extent, to first order, a coarse grained sand and a medium grained sand, if they have the same porosity, will look the same elastically. And so that's been the headache. So I just want to emphasize here that porosity alone does not determine permeability, it's also the particle size. And of course, if there's fractures present, certainly in these tight rocks, they will tend to dominate the permeability. For unconventional gas shale resources, fractures are essential. They provide the drainage surfaces, and these can be naturally occurring fractures or fractures that you make with treatments. And we'll also point out that although many times fractures are good, fractures can also harm production by introducing too much water in the case. So one project I did for a company working in the Barnett, the goal was to find fractures, but not too many fractures, because the highly fractured zones produce water too quickly. I'm sure you've encountered that. Even in the Gawar field in the Middle East, the biggest, easiest oil field in the world, has water problems generally associated with the presence of natural fractures. Now, when you introduce fractures into a rock, certainly they impact permeability, but they also have a lot of seismic attributes that people have discussed for a long time. When we introduce fractures in a rock, we tend to lower P-wave velocity, lower shear wave velocity. We tend to change the V-PDS ratio because P and S waves respond a little bit differently to fractures. We tend to increase the wave attenuation when fractures are present. And depending on their alignment, we may see some seismic anisotropy. In the literature, people have mostly focused on looking for anisotropy as an indicator of fractures. That's kind of the sexy one. But I wanted to remind you that there are a lot of isotropic signatures of fractured rock too. Sometimes they're even stronger.
That's why you made all the fractures vertical.
That was the limit of my drawing skills. But they're not always. There's not always vertical. Many times when I've been involved in projects, they were vertical fractures. It has to do with the in situ stresses and so on. So here would be a case where maybe the vertical stress is bigger than the horizontal stress.
That's kind of still a simplistic answer because there's a whole lot of difference in the rock strength.
Sure, yeah. When really diving into this, we would have to, if we were looking for fractures, we would want to start with the best a priori model, which is what do we know about the depth, the stress field, the fabric of the rock itself, and so on. Thanks for bringing that up. Now, what I'm going to do when I flip the slides is just in cartoon fashion talk a little bit about changing in the effective stress. So what I mentioned on the right here is, for example, high pore pressure or low effective stress helps to keep fractures open. Now, if I were to drop the pore pressure, the effective stress increases, and there's a tendency for these open fractures to be closed. That's just kind of an elastic effect. And to some extent, it can be kind of reversible, not exactly. And so that's another key too, is when finding fractures, they can be useful, but the extent of their usefulness sometimes over time depends on how much pressure maintenance there is in the system. I worked in a Powder River Basin project once where, I guess it was the Niobrara, a long time ago, and ARCO and Amoco were working with us, and there had been a well drilled, and a lot of gas was found with really good flow, but if the flow petered out in about a month. And then there was some magical geologic boundary there. If you went about a mile to the south, drill the same formation, same depth, and the flow lasted for a long time. So the overpressure and its maintenance is also very important. And to some extent, we might see that in the seismic data. Now,